Good morning, everyone. The topic which we are going to cover today in Dbms is the deadlock handling in Dbms. It is deadlock. The concept of deadlock is very much similar as you people have seen in operating system. But the thing is that now we are going to discuss this concept in terms of transactions. So when we go with the deadlock in the transaction in the Dbms part, then the algorithms which you have seen over there, it is totally different here. So what is a deadlock? The proper definition of deadlock, what it says, the system is deadlocked if there is a set of transactions such that every transaction in the set is waiting for any transaction in the set. For example, if I am having these three transactions, T1, T2 and T3. Let's suppose T1 wants to work on data item A, T2 also A and B, it also wants to work on A and B, and this also wants to work on A and B. Now what will happen if this transaction T1, it held this data first and this transaction also held this data, and we had applied the two-phase locking protocol. In that case, this transaction T1, it will get a lock on data item A, and transaction 2, it will get the lock on data item B. Now later on, transaction T1, it wants to acquire or it wants to work on data item B, but it is not possible. Why? Because T2 has already got a hold of this data item B and it has not released this data item yet. So what will happen? It will go in the waiting state, and whom it is waiting? It is waiting for the T2 transaction. Now see what happened here. After some time, your T2 transaction, it also send a request for the data item B, but and this data item A is already being acquired, is under your transaction T1. It is already working on this data item A. So here the T2 transaction will go in the waiting state on this particular data item A. Now it is waiting for T1. So T1 is waiting for T2 on the data item B. T2 is waiting for T1 on the data item A. So there is a deadlock kind of thing because no transaction is proceeding further. Their execution, it become halted. There is no progress in T1 and T2. So this is my deadlock condition. Now look here at T3 and at T3. So now since already T1 and T2, they had got the hold of A and B, T3 also wants to get hold of A and B, but due to the locking protocol, T1 is not able to release the lock on A. Why? Because it is still waiting to get a lock on B. Similarly, so here T3, it will go on waiting state for this data item. So T3 is waiting for T1. Similarly, T3 also wants to work on B, but B is currently locked by transaction T2. So T3 is waiting for T2. But here, if you look at the figure, your T1 and T2, there is a cycle. They are waiting for each other. But in the case of the T3, there is no formation of the cycle. That is, although T3 is waiting for T1, it is also waiting for the T2. But the thing is that T1 is not waiting for T3. Similarly, T2 is also not waiting for T3. So in this deadlock scenario, only the deadlocked transactions, they are T1 and T2. They are only T1 and T2 and not T3, although the progress of transaction T3, it depends upon T1 and T2. My system is in the deadlock state, and the 3 transactions in this deadlock state, they are not able to progress further. T1, T2, T3, they are not able to progress further. But if I want to identify that the deadlock has happened due to which transactions, who are the main culprits who are involved for this deadlock state, then T1 and T2 is the answer. If we talk about the real world example, for example, in online ticket booking system, suppose that I am having 2 users, user A and B. They are attempting to purchase the tickets for the same event. Here the transactions are referred to as 2 users, and the resources are the seat selection and the payment processing. How the deadlock can happen in this system? User A selects a seat by booking the seat and moves to the payment portal. User B selects the payment portal and then tries to change the seat. Then in that case, user A is waiting for the payment system and user B is waiting for the seat selection. These are the 2 separate modules, and in that case what will happen? Both are waiting for each other to release the lock, and therefore in such a situation the deadlock will happen. This is another example. Suppose we are having the transactions. T1 is having 2 instructions, write instruction on X as well as write instruction on Y. Similarly, T2 is also having the instructions write Y and the write X, and this thing is very much similar to the previous example. But here what we have done, we have generated a schedule in this case. Schedule, that is, when I generate a schedule, then there may be certain schedules are in such a state that no deadlock will happen. But if I look at this schedule, then this schedule will lead to a deadlock state in the system. So now my main aim is to identify such schedules which may lead to a deadlock state, and we need to avoid these schedules, that is the transactions, they cannot occur in the order which has been described in that particular schedule. So if in this schedule what is happening, T1 has applied the lock X on A, exclusive lock it has obtained on A, and it has start writing on A. Similarly, T2 transaction, since it need to work on first on Y, so here what will happen? Sorry, this is exclusive lock on B, that is, this is my A, this is my B, and this is the schedule. So, and it start writing the data item B. Now it need to work on A, so it will send a request for exclusive lock on A, but it will not get this request fulfilled due to my locking protocol. Lock X, because already there is exclusive lock A on A, so this is uncompatible locks. So the transaction T2, it will not get the lock on A. Similarly, T1, when it is proceeding, it tried to acquire the exclusive lock on B, but still it didn't get it due to the same reason which we have seen as in the case with the data item A. So now the question comes, how we will handle the deadlock in Dbms. So very first algorithms which we are going to discuss is the deadlock prevention protocols. And what are the prevention protocols? They ensure that the system will never enter into the deadlock state. So some prevention strategies will need to take into consideration. What the prevention algorithms say? They say that we will never let our system go into the deadlock state before actual running of the transactions on the database. It's best to first see whether our system will go into the deadlock state if we go with the actual execution. So here, how we can see how we can prevent the deadlock? Require that each transaction locks all its data items before it's begin its execution. So pre-declaration need to be done here. Whatever the data items I'm using, I need to pre-declare it. So as in this case, what is happening? We are acquiring the lock at different stages. So, pre-declaration, what it says, that acquire the lock on the early initial state. That is, here after lock, exclusive lock, lock X on B also. So now what will happen? It has transaction T1, got both the locks. So in this case, it will never go in the waiting state. Now here again T2, it also the same scenario case goes with the T2. So also T2 also need to acquire both the locks. So it will give the permission first on lock X on B, then lock X on A. Now what will happen? For this also it will go in the waiting state, and for this also it will go in the waiting state. Now once your transaction T1, it finishes its transaction, it will release both these locks and transaction T2 will start its execution. So here the transaction T2 never waiting for the indefinite time for the transaction T1. There is a progress after a deterministic time in the case of T2. Other scheme says impose partial ordering of all data items and require that a transaction can lock data items only in the order specified by the partial order. That is, whatever the data items are there, we need to create a hierarchy. The things which we have seen in the multiple granularity, the same schema we can adopt here also. That is, we need to identify that in which order the locks can be acquired in the data item. For example, if I am using this data item, then I cannot acquire the lock on this parent data item. But yes, if I am working here, then I can send a request for these data item locks. So following schemes use the transaction timestamps for the sake of deadlock prevention alone. So in this prevention schemes, we are using the timestamp values. The very first scheme is the wait die scheme. Wait die scheme is non-preemptive, whereas wound wait scheme is preemptive in nature. What the wait die scheme says, that is, it says older transaction may wait for younger one to release the data item. That is, older, how we are going to identify these are the older transactions, these are the younger transactions with the help of their timestamp value. That is, at the time when the transaction got initialized, a timestamp value got attached with that particular transaction, and that timestamp value is being used to recognize whether that transaction is older or a younger one. And why we use this? Because we say that the younger transaction never wait for older ones, they are rolled back instant. So a transaction may die several times before acquiring the needed data item. Here what we are saying, for example, I am having transaction T1 and T2. This is old transaction and this is my young transaction. So in this case, I am saying if T1 is working on A and T2 also wants to work on A, then we say that T2, it may wait for the T1. But if T2 has acquired or using the data item B and T1 also wants to work on this data item B, but it is not available instantly, then we say then they may wait for the younger one to release the data item. That is, younger transactions, they never wait for the older ones. That is, if it go in the waiting state, then it need to be rolled back. But if T1 is waiting on the data item B, in that case, it never rolled back. Also, a transaction may die several times before acquiring the needed data item. So, it may lead to the condition, that is starvation. Another scheme is bound wait scheme, and it is a preemptive scheme. What it says, older transaction bounds, that is, they are to be rolled back of the younger transaction instead of waiting for it. Younger transactions may wait for the older ones. That is what we are saying. We are saying that if T2 is waiting for the T1, then it is allowed. But if T1 is waiting for T2, then it is not allowed. Why? Because it is the older transaction and it need to be rolled back in this case. So, it is my preemptive, that is we are forcing the rollback. Maybe fewer rollbacks than the wait die scheme. Why there is a possibility of, because in the case of the older transactions, it has acquired many variables during its life cycle, and now it is nearing to about its exit point. And what we are saying, younger transaction, they have just come into the system, so they need the data item which is already being held by my T1 transaction. And if I am not rolling back my younger transaction, what I am doing, I am rolling back the T1 transaction, that is the older one. So in that case, fewer rollbacks they are required. So in the case of the wound wait, we are having fewer rollbacks as compared to the wait and die scheme. Both in wait die and in wound wait schemes, a rollback transaction is restarted with its original timestamp. Older transactions thus have precedence over the newer ones, and starvation is hence avoided in this case. Timeout based schemes, a transaction waits for a lock only for a specified amount of time. If the lock has not been granted within that time, then the transaction is rolled back and restarted. There is no concept of old and young transactions. Thus, deadlocks, they are not possible in this case, because let's suppose I am saying that my waiting time is 5 seconds, then every transaction it is coming here, it is, if that transaction is going in the waiting state, then it will wait only for the 5 seconds, and within the 5 seconds, if it get hold of that data item, then it's okay, it will continue its execution. But if it don't get that data item, then it will roll back. It is very simple to implement, but in this case, that is no deadlock is there, although no deadlock, but it may lead to the starvation. Also determine the good value of the timeout interval, that is whether my time value, I should keep it minimum, what should be maximum, either it should be average, what value should be there of my timeout interval. It is a debatable question and it depends upon the type of transactions they are coming in my data, the type of the data item on which we are working. Another set of protocol is the deadlock detection protocol. In the deadlock detection protocol, we use the wait for graph. In the wait for, as in the graph, we are aware that we are having the vertices and we are having the edges. So we are having a set of vertex, we are having a set of edges. Now in this case, vertex, it is a transaction, that is my transaction is being represented with the help of circles, and on the edges we are representing that the transaction is waiting on which data item for the transaction 2. So V is a set of vertices and E is a set of edges. Each element is an ordered pair, that is Ti to Tj. Now when question comes how we insert this edge between Ti and Tj. So if Ti, Tj is in E, then there is a direct edge from Ti to Tj, implying that Ti is waiting for Tj to release a data item. When Ti requests a data item currently being held by Tj, then the edge Ti, Tj is inserted in the wait for graph. This edge is removed only when Tj is no longer holding a data item needed by Ti. That is, there is no waiting condition between Ti and Tj. So that data system is in a deadlock state if and only if it contains a cycle. Must invoke, and for this we need to invoke the deadlock detection algorithm periodically in the system to look for the cycles. For example, this is the wait for graph without a cycle. Although T7 is waiting for these two transactions, T19 is waiting for T18, T18 is waiting for T20, but still there is no cycle, so no deadlock. Whereas in the case of this graph, what is happening? T17 waiting for T18 and T19, T19 waiting for T18, T18 waiting for T20, but look at this edge. T20 is waiting for T90, so there is a deadlock. In this case, there is a cycle, so there is a deadlock. This is another example. I am having these sets of the transactions. If you look here, what is happening? From here, this is the cycle we are having. Whereas in this, there is no cycle. So if I need to identify, because once the deadlock is being detected in the system, then I need to go for the implementation part to break this deadlock. So for breaking the deadlock in the system, I need to identify what transactions they are being involved here. So in this case, always remember that when the cycle, transactions in which the cycle has been formed, they are the victims. So we need to select among them. So in this case, the cycle is being formed here. So we need to select the victims among these. They are not being selected as the victims. This is an example. Suppose that at some time during the execution of a database, we have the transaction scenario. And in that case, we are having 5 transactions. These are the data items being logged by the transaction. And these are the data items each transaction is waiting for. That is, T1 has acquired the lock on B, but it is waiting for the data item A and C. Similarly, T2 has got the C, but it is waiting for D and E. If you look here, so what is happening? T1 is waiting for T2 on the data item C. Clear? Similarly, A, it is waiting for A. Who has got the A? T5. So T1 is waiting for T5 on the data item A. Now T2 has got the C, but it is waiting for D and E. Now look here, who has got this D and E? D and E. E is with T3. So T2 is waiting for T3 on which data item? On data item E. Similarly, E is being held by, E is being held by T3 and D is being held by T4. So here we are having the T4 and your T2 is waiting for T4 on data item D. Now come on T3. T3 has got E and F, but it is waiting for G. Who has got G? T5 has got G. So here T3 is waiting for T5 on the data item G. T4, it wants to use A. Who has got A? Your T5. That is, T4 is waiting for T5 on data item A. Similarly, T5, it has got A and G, but it is waiting for C. Who has got C? T2 has got C. So, T5, it is waiting for T2 on data item C. So, this is the rough diagram for, this is my wait for diagram for this particular, wait for graph for this particular case study. So, here, this is exactly what I am getting. If here I look, I am having a cycle. So, if I go here T1, T2, T3, then T4. So, T2, T3, T5 and then T2. So, there is a first cycle. Now, look here T2, T4 and T5. There is a second cycle in this case. T1, T2, T3, T5, no cycle. Then T1, T2, T5 and T1, no cycle, T1, T3, T5, no cycle. So now there is no, these are the 2 cycles. So for the we have detected the deadlock. Now I need to break this deadlock. So the chances, these are my victims. Clear? So for breaking the deadlock, we need to roll back these transactions. So now the question comes, we have detected the deadlock. How we will recover from the deadlock when deadlock is detected? Some transaction will have to roll back, made a victim to break the deadlock. Select that transaction as a victim. That will incur the minimum cost. And what is the criteria for the minimum cost? How many variables they have used, how much processing time they have used. These are the certain criteria on the basis of which we select the victim. Rollback, that is, it determines how far to roll back. That is, either we go for the total rollback or the partial rollback. That becomes the question. Starvation happens if same transaction is always chosen as a victim. So we need to include a factor, that is how many times a transaction is going to be rolled back. So these are the deadlocks. If we have a drawbacks, if we have the deadlock in a system, transaction stalling is there, system resources are wasted, inconsistency in database may be introduced, and the transaction rollback increases. So the deadlocks, they are not good for my transaction system. These are the references which I have used. So in this particular lecture, we have discussed the deadlock. What is a deadlock? How it can be prevented and how it can be detected. Once it is detected, how our system it can be recovered. Thank you and Jai Hind.